Hello everyone! In this short video, we will see how wind loads derived from the Eurocode are applied to our parametric Karamba3D example of a duopitch canopy roof. If you missed part 1, looking at the geometric definition, or part 2, looking at the wind load derivation, please go back and check out the previous videos. If you want to hang around instead, here's the quick summary. Part 1 describes the parametric geometry setup for a duopitch canopy roof. This is based on a few simple input values and prepares the model for analysis. Part 2 focuses on the specifics of wind load calculations by following the Eurocode clauses and deriving the force coefficients within our parametric setup. Part 3, which is what you're watching now, is all about putting everything together to define code-compliant wind loading on our example for analysis and design. Let's begin with the basic requirements presented in Part 2. The Eurocode prescribes 6 load situations for a duopitch canopy. We must analyze for pressure on both sides at the same time, pressure on each side individually, suction on both sides at the same time, and suction on each of them individually. In terms of parameters, we have geometric inputs which define the shape and the angle of the canopy. We also have the degree of blockage going from 0 to 1. And finally, we have QP, the peak velocity wind pressure in kilonewtons per meter squared, a parameter which we have not yet used. We should also remember that the main goal of the previous video was to determine CF_min, representing a net upward force, i.e. suction, and CF_max, representing a net downward force, i.e. pressure, for our given geometry and blockage. Now, with everything set up, we apply the following procedure. We take our inclined canopy areas and determine the uniform area wind loads that we must apply in the 6 loading situations. Essentially, we use the QP pressure multiplied by the force coefficients to determine the UDLs. For load application, we make use of the constant mesh load component, and we use the load case combinator component to derive SLS and ULS combinations. What is crucial is to use Grasshopper's data structure logic to create everything in one go using data trees. Let's look at the implementation steps. Step 1. Mesh definition. First, we have to set up our loading meshes. We want to have 2 meshes, one for each inclined surface of the canopy. We take our roof beams and filter out the outer beams and the central beam. We then create an ordered list of those 3 beams and apply a simple shift followed by a shortest list component to achieve the pairing of outer beam left to central beam and central beam to outer beam right. We loft those 2 sets of curves to obtain 2 flat roof surfaces, and we use mesh UV on both of them. We select a relatively coarse mesh, in our case with 6 and 30, but this is parametric and can be modified to suit. Step 2. Load direction. We need to define the loading direction, and for this we can use the mesh normal. We get the mesh centroid, get the mesh closest point to that centroid, and use the evaluate mesh component, which also outputs the normal vector at that point. So effectively, we get one normal vector for each mesh. We want the normal vector to point downwards, so that using positive values for pressure, the load vectors are downwards, and using negative values for suction reverses the vectors and points upwards. We achieve this by utilizing the dot product between global z direction and the normal vectors. For negative dot products, we maintain the orientation, i.e. downwards, and for positive dot products, we reverse the vectors. Step 3. Load magnitude. The load magnitude is defined simply by multiplying our CF coefficients with the peak wind pressure QP. However, in this step, we also take care of the 6 load situations mentioned earlier. We can see this happening inside this small cluster that takes our CF_max and CF_min as inputs. We aim to create a tree structure with 6 branches, one for each load situation. Within each branch we have 2 force coefficients that apply to the left and right meshes. Using a series of tree operations and 3 values, CF_min, CF_max, and 0, we can achieve our goal. You can see here the result and structure of the data. We can also see here the final UDL values structured accordingly. Step 4. Load application. The final piece of the puzzle is the mesh load component itself. We want to create a set of mesh loads and apply them to the two sides of the canopy on the secondary beams alone. This is key, and in part 1 we have defined beam IDs to help with this. The IDs split the beams into secondaries left, secondary central, and secondaries right. At this point, we need to coordinate everything based on the load situation. And furthermore, we must set up different element IDs to be loaded according to the mesh being applied to, i.e. left mesh or right mesh. Therefore, our UDL vector, loading mesh, element ID, and load case inputs are structured in a tree format with the load situation on the first index from 0 to 5 and the mesh on the second index from 0 to 1. In total, we have 6 times 2, i.e. 12 branches. First, the vector already comes in 6 branches, with 2 items per branch corresponding to left and right. So a simple graph gives us our desired outcome. Secondly, for the mesh, we start with a simple list containing our 2 meshes. We duplicate this based on the number of vector branches, 6, and partition that list into sets of 2. We graph this to get the same structure as above. Next, element IDs start out as 2 lists of 2 IDs. Secondaries left and center in one for the left mesh, and secondaries center and right in the other one for the right mesh. We entwine this to get 2 branches, which we duplicate based on the number of vector branches. We partition these 2 branches into sets of 2, but the structure is reversed, with the mesh index first and load situation second. Using PathMapper, we flip the structure to match everything else. Finally, we define 6 load case names for our load situations using simple indexing from windload 0 to windload 5. We duplicate and partition this based on the fact that we have 2 meshes, and again we obtain the same structure. By looking at the data, we see that, for example, for branch 1, 0, we define load case windload 1, in which we apply a vector downwards onto secondaries left and secondary center. But for branch 1, 1, also in load case windload 1, we have a vector of 0 applied onto secondaries center and right. This corresponds to the pressure on one side situation. Checking through all the branches, we can see that the 6 load situations are appropriately defined. For the mesh load itself, we ensure that we have mesh load constant selected. We select global as our orientation since our vectors are globally defined, and we want to generate only line loads on our secondaries, so we only tick this radio button. We also specify that we want 1 load per element in order to generate uniformly distributed loads on the secondaries. Finally, using the load combination component, we can set up the rules for SLS and ULS. We can group wind loads 0 and 1 and 2 into wind pressure, and wind loads 3, 4, and 5 into wind suction. We then combine them into a single load combination called wind, or W, and we use this in the SLS and ULS expressions with a factor of 1 and 1.5 respectively. This concludes our 3-part series on this example, where we have delved in depth into setting up a parametric duopitch canopy roof example and used Karamba3D to analyze it to full code-compliant wind loading as per the Eurocode. Let us know what you think about this series, and if you want to catch more content like this, please remember to like and subscribe.